Hi everyone. Today we will continue also with convolution, and we will finish the chapter 6. Okay, so last time we talked about convolution and convolution of two functions is defined by the integral in the following way, from 0 to t. So f inside we write t minus u and g of u du. So this was the definition of the convolution, and we know that convolution is commutative, so it doesn't matter which one you write first. And we also said it's associative, so if you have more than one convolution, so you can start from any one. And furthermore, the main property of the convolution was the following, why we were defining and using it basically. So if you take the convolution of two functions, and if you take it to Laplace, basically the product of the Laplaces. So f's Laplace times g's Laplace. And furthermore, we learned that if you convolve with the delta function, and if you convolve anything with the delta function, so you can use this notation or this notation, they are both fine, but not any delta function at 0, then it's the same as the, this was in the proof, so we prove this thing. So f convolution with delta at 0 is equal to f. So basically delta at 0 is the identity element of this operation. Okay, so now let's do some examples of convolution. So let's look at one convolution 1. Let's try to do this. So first example. So by definition, from 0 to t, in the first function I plug in t minus u, but it's constant function, so I get 1. In the second function I plug in u, it's again 1. So du. But then this is equal to just integral of 1, which is u, from 0 to t. So we get t minus 0, which is t. So convolution of 1 with 1 is just t. Actually, we could do it in the another way. So let's say that I want to find this. So how I could do this? I can use the convolution theorem, which says that 1 star 1, so Laplace is equal to Laplace of 1 times Laplace of 1. And I know the Laplace of 1, which is 1 over s, and then this is also this, 1 over s squared. So it says that whatever this thing is, its Laplace is equal to 1 over s squared. So I know 1 over s squared, if you apply L inverse to this, then we get t. So if you apply L inverse to this side, then we get 1 star 1. So it says that Laplace of 1 star 1 is 1 over s squared. If you just apply L inverse to both sides, 1 star 1 must be t, which is convolution of 1 with 1. Okay? So actually you can do more. Yes. So if you look at 1 star 1 star 1 star 1, how about this as a second example? So we know that convolution is associative, so it doesn't matter which one you do. And so you can just you can group them and then continue. But I will just, if you do this thing, and I will rather, you can do one by one, but I want to do it directly by using the second method I did. So if you look at, if you take the L of this, then this is L1 times Laplace of 1 until the last one. And from this side, we know that this is 1 over s, this is 1 over s. So eventually, we get that this is 1 over s to the n. So if you write here n many. Okay. So then we have 1 over s to the n. And so then what is this? So if you take inverse Laplace here, and it must be the same as inverse Laplace of this one. Okay. So inverse Laplace of this one, we know it is, so I'm applying inverse Laplace to everything here. So Laplace is taken, I'm just taking its inverse. So I get 1 star 1 star 1. Okay. So what I get, so it's all about what is happening here. So this is s to the n, and I want to use the formula. So I remember this thing from somewhere. So if it were n plus 1 and here n factorial, I know the answer. So I will just play with this. So this is n, and I need to write here now, if I write here n minus 1 factorial and divide by n minus 1 factorial. So if you look at this portion, this is exactly Laplace of t to the n minus 1. And so divided by n minus 1 factorial. So t to the n divided by n minus 1 factorial. This is what we get. Okay. Maybe second example. How about two exponentials? Maybe, okay, let's do e to the 2t star e to the 3t. So how about their convolution? So if you look at this, this is from 0 to t. In the first one, or in the second one, it doesn't matter. I write t minus u in the place of t, and multiply with e to the u d, and then I integrate. So if you look at this, we get from 0 to t, and we have e to the 2t, e to the minus 2u, e to the 3u du. So I'm integrating with respect to u, so that means this is constant with respect to integration. So you can take it out. We have e to the 2t, and from 0 to t, if you add the exponents, so we have just e to the u du, which gives me e to the 2t times e to the u from 0 to t. So this is what we get. And from here, we get e to the 2t, and we have e to the t minus e to the 0. So eventually we get e to the 3t minus, this is 1, so e to the 2t. So you get their difference. All right. You could do by the second method. First of all, take the Laplace and then take the inverse. Okay. Let me apply that method to the following one, because as a third example. So how about Laplace of u2, so I'm sorry, a convolution of u2 with, let's say, u5. How about this one? This time you can still do the definition, but it may be a little bit complicated because, not complicated, but it may take more time because these are step functions. You have to do case by case. So rather than doing that, I will just apply the convolution theorem, which says that whatever this thing is, its Laplace is equal to product of the Laplaces. Okay, so product of the Laplaces. So I know this one and this one. So this is going to be e to the minus 2s times 1 over s times e to the minus 5s times 1 over s, and which is equal to e to the minus 7s times 1 over s squared. Okay, now we got the result. So now I take inverse of this, which will give me the inverse of this. So if you take the inverse, this is u2 convolution u5, and if you apply inverse to this, so we know e to the minus cs formula, so this will give us a step function now, this time at 7 times, I need to take the inverse of this, but then I have to shift it. Its inverse will be t, but it must be shifted with amount of 7, so we get t minus 7. So convolution of the two step functions u2 and u5 gives you this thing, so they are equal to each other. Okay, so these are equal. All right. Now, where do we use this result? So basically, I mean, we use convolution to write the solutions. So for certain differential initial value problems, rather than taking the inverse of them, because it may be very complicated, we can write our answers by using the convolution. So then, let me do an example for it. Basically, that's the main purpose of this for the initial value problems, which allows us to leave the answers in terms of convolution operation. All right. Now, so we have the third derivative minus the second derivative plus 2y equal to, on the other side, cosine 2t plus the delta function at 21 and y0 and y prime 0 are equal to 0, and but y double prime 0 is given as 1. So the question is, use convolution theorem, to solve IVP, this initial value problem. So whenever we see this, we understand, I mean, we can write our answers, or we can leave our answers in terms of convolution operation. Okay, now what I'm going to do, it's third order, but it doesn't matter. So we apply, solution. We apply Laplace to this equation. So I'm taking the Laplace of both sides, so it's linear, so I can separate it. Okay, so if you look at this part, we have third derivative, so we have s cubed times y of s minus s squared times y0 minus s times y prime 0 minus y double prime 0. That's just the Laplace of the third derivative minus Laplace of the second derivative, which is s squared y of s minus s times y0 minus y prime 0. Okay, plus 2 times Laplace of y, which is y of s. On the other side, we have Laplace of cosine t, so this is going to be, we have s squared here and 2 square s here. Remember, s over s squared plus a squared. And Laplace of the delta function is e to the minus 21s. That's what we have. All right, now let's put the knowns, which are the initial values. And luckily, I mean, we have y0 is 0, y prime 0 is 0, but this y double prime is 1. Again, now this is 0, this is 0. So from this now, we get in y of s parentheses s cubed minus s squared plus 2. But then there's only one non-zero term left. That is this one, which is minus 1. So I will take it to the other side. Okay. So if you look at this, in y of s parentheses, we will have s cubed minus s squared plus 2. The other side now, 1 goes there. So we have 1 plus s over s squared plus 2 squared plus e to 21s. So after dividing, we have 1 over s cubed minus square plus 2 plus 1 over s cubed minus s square plus 2 times s over s cubed minus s square plus 2 and plus e to the minus 21s times 1 over s cubed minus s squared plus 2. Okay. So what we would do previously, I mean, we have to, sorry, this was, okay. So this is supposed to be the cosine's Laplace. Sorry for that. So this is s squared plus 2 squared. Okay, so typically, I mean, we were using partial fractions and then using the inverse of the Laplace to find the solution. But if you try to do that way, it will take a long time. But now since we are allowed to use the convolution theorem, we can leave our answers in just using the convolution. Okay, now let's look at this operator, because as you see, like this 1 over s cubed minus s squared plus 2 everywhere. So how about its factorization? If I can factorize it, then I can use maybe its factorization to write the answer. So how is the factorization of s cubed minus s squared plus 2? let's look at this one. So what we can do here, if there is an integer solution to this, then it must divide 2. So it will be either plus 2 minus 2 or minus 1 plus 1. So if you plug in 1 here, we have 1 minus 1, 2, so it doesn't satisfy that one. If you plug in minus 1, then we have minus 1 here. So we have, again, now minus 1. So we have minus 1 here, minus 1 here. So we have minus 2 plus 2, so we get 0, which tells us here minus 1 is a root of this, which says that in the factorization, there should be an s plus 1. Okay? So minus 1 cube is minus 1. Minus 1 square is 1. So minus here, we have minus 1, minus 1, minus 2. So this is what we see. So I can factorize s plus 1. So what is left is, since it's third degree, there must be a second degree polynomial here. So since the constant is 2 here, there is 1. So our constant must be 2. Since we have s cubed, so we must have s squared here. So it's all about the s term here. Now let's try to see that one. And so if you look at what is the coefficient here, so we must have minus s squared here. So let's try to arrange it. How do I get minus s squared? So s squared times 1, and this s times s will give us s squared terms. If I want to get minus s squared, then this must be minus 2, because s squared times 1 minus 2s times s, if you add them up, this is what you get. So, and this can be written, obviously, s plus 1 times s minus 1 square plus 1 square. Okay? And so now, I'm going to use this factorization to compute the inverse in terms of convolution. Okay. So now I can write y of s in the following way: 1 over s plus 1 times s minus 1 square plus 1 square plus, again, the similar thing we have, s plus 1, s minus 1 square plus 1 square times s over s square plus 2 square plus e to the minus 21s times 1 over s plus 1 s minus 1 square plus 1 square. Now, what is yt? Yt is the inverse of this, which is, now, if you use convolution, so here we have 1 over s plus 1 and 1 over s minus 1 square, 1 square. So 1 over s plus 1 is e to the minus t if you take inverse. So this one, now I convolve this with the inverse of this one, which is obviously, this is a sine, but there's a shifting in the s domain, which means it is multiplied with exponential in the time domain. So if you write e to the t sine t, okay, so its Laplace will be this. Then now we can continue. So this time I will have the same copy, but this must be, there will be three terms. So we will have e to the negative t convolution e to the t times sine t convolution. So we know that this is cosine 2t plus, now the final one you can just take it back. It's up to you, actually. You can write this portion as 1 or just 3 of them. So which is delta at 21 convolution e to the negative t convolution and e to the t sine t. So this was the main purpose of introducing such notation. So this allows us to write our answers in terms of convolution. Otherwise, if you want to, furthermore, if you want, you can compute them, or what you could do, basically, you can write them as partial fractions. You can compute all those coefficients in the numerators to give you equality, but it will take really long time. But this allows us to write the solution in terms of convolution. Also, it helps us to solve certain integral equations when we are given an integral equation rather than a differential equation by interpreting the given integral as a convolution. So let me do a simple example for the sake of completeness. So now we are given the following, this problem in the book, I guess. So we are given such thing, and this is integral differential equation. So there is an unknown function and there's an integral in it. So we have p of u du, and that's equal to t. Okay, and we have the initial value given as 0. Okay, so the problem is, find phi which satisfies this initial value problem. Okay, so now if you look at this one, now I'm going to use again Laplace transform. So if you apply Laplace to both sides, so this time let me be quicker. So I will just apply the Laplace to this problem. So I will apply Laplace to this side, and also I will apply Laplace to this side. So I know if I apply to this side, I get 1 over s squared. So if you apply to this side by linearity, this will give you s squared, so s, it's first order. So let me call its Laplace as capital phi of s minus phi 0, small phi, plus. Now it's all about finding the Laplace of this portion. But if you look at this, is not this is a very actually nice integral because it's actually a convolution of two functions. And what are those functions? Actually, if you look at the definition, you are basically convolving phi, your unknown function, with the. So if you look at in a function, you are writing t minus u, and you are getting t minus u. So that function must be t. So this is just the convolution of t with phi. So if you apply Laplace to this, then we get Laplace of t is 1 over s squared times, because it's convolution after Laplace, it's the product, times Laplace of phi, which is capital phi of s. Okay. Now let's put the initial condition. So phi 0 is 0. So from this part, we get the following. If you take phi of s, capital phi of s, parentheses, then what do we see? We see the following. Phi of s, parentheses, Okay, and s here plus 1 over s squared. The other side, we see 1 over s squared. Okay, and so if you write this, this is going to be s cubed plus 1 divided by s squared. Now the other side is 1 over s squared. So this gives us phi of s is equal to, if you divide 1 over s squared with this, s squared will come here, s cubed plus 1 to the bottom. So we have s squared cubed plus 1. So these are cancelling. So eventually we get 1 over s cubed plus 1. So the solution's Laplace is 1 over s cubed plus 1. So then it's all about factorization of 1 over s cubed plus 1. Let me write just the factorization and leave the rest to you. So you can leave your answer eventually as the convolution of two integrals. So two functions. So phi of s. Now if you know the factorization, this is 1 over s plus 1 times 1 over s squared minus s plus 1. Okay. So what you're going to do, so we know this, actually we did in the previous example, we know this one. If you want to use the convolution theorem, if you it's just e to the minus t, it's all about this one. So again, you can write this thing as the sum of squares. Let me maybe write it. S minus 1 over 2 square. So if you take the exponent, if you expand it, we get s squared minus s plus 1 over 4. So there should be here radical 3 over 2 square. If you take it square, we get 3 over 4. Add 1 over 4, you get 1. So this is what you get. So basically, this part will be again shifted. It's shifted. The shifting is an amount of 1 over 2. So in the time domain, there must be an exponential with 1 over 2t. And as you see here, since there is no s here, this is just a sine function. Okay. You can do the rest of it. Now, I want to talk about the meaning of convolution a little bit. And then after that, I'm going to finish the lecture. So why do we really care about this operation? So if you now let me just talk about this for the second order. Actually, you can do for every order, but let me just do it for the second order. So what do we do for the second order? Let's say we have given a constant coefficient, second order differential equation. Okay. And on this side, let me just check the notation I'm using. Okay, G, so okay, G, the forcing function. Then let's say we have the initial values. Okay, so I used y0, y prime 0 is y1. Then what do we do to solve this problem? So let me just maybe, okay, let me just do the more general. So let's say a y double prime b, so c. So what do we do now when we use Laplace? So this will give us an something in terms of s, and then also we take the Laplace of this. we solve the problem and then we take the inverse Laplace. All right. But now, if you do this thing, then what do we get from here? So we know that we will get y of s if you apply Laplace. In its parentheses, we will get a times s squared plus bs plus c. And also we will have from the second derivative, we will have minus s times y0 minus y prime 0. From here we will have minus y0 also with b coefficient and this a coefficient. So now if you take them to the other side, then we will get the following. We will have a times s times y0. Now y0 is y0. And then plus also a times y prime 0, which is y1. And then from this one, we have minus b times y0. So we have y0 to the other side. And plus Laplace of this, g of s. And then now we have then y of s is equal to this one. Now if you take y0 parentheses, as plus b, and plus a y1 parentheses, maybe if you write this, a1 divided by as squared plus bs plus c, and this is 1 over as squared plus bs plus c times g of s. So then after this, what do? We apply inverse Laplace, and so we get y of t, which is inverse of this capital Y, and we will take the inverse Laplace of this, and we will take the inverse Laplace of this one. So then we will get two functions. So let's say this one will give you a function of t, and this one will give you another function of t. So so after L inverse, applying L inverse. All right, now let's do something practical to understand it further. So if I assume that my initial conditions are both 0, this is y0 is 0, y1 is 0, so then what do I get if my initial conditions are both 0? Then this part will go away. So what you will have is the following portion. Okay? So assuming now y0, y1 both are 0, then our solution is going to be this P, which is actually L inverse of 1 over a s squared plus s plus c times g of s. But which can be written now, since this is a product, I can write this thing in the following way: L inverse of 1 over a s squared plus bs plus c convolution g of t. So what do I understand from this? I mean, if you forget about this portion of the problem, if you forget about this if you forget about this portion of the problem, if you just think about this portion, what this thing says, actually, if you want to find the solution under these conditions where the initial conditions are 0, it's all about convolving your forcing function g with this thing. Okay? So in my equation, so if this part is fixed, but if this part, if I'm using different forcing functions, so then it's all about knowing this solution, which says that whatever the forcing function is, the result is always convolving the forcing function with this thing which is fixed when you are given the differential equation. So you can think your differential equation like an operator, and this is like a signal you put in your operator, and then you want to understand the outcome. The outcome is the solution, basically. It says that you put the signal g, the output is always convolving g with the operator, or with the processor, maybe you can say, of the differential operator, differential equation. So if you want to, symbolize it in the following way, and if you want to, the following way, so this is your differential operator. You can think like this is your a y double prime plus b y prime plus c y. Okay, and so now your forcing function may change. You can think like your forcing function as an input signal, and you want to understand the output. Okay, so the output for this one. So for every forcing function, you want to understand what is the solution under 0, 0 initial conditions. It says that, so your differential equation will give you a processor, and you put your signal, and the output is your solution. But output is, here, the output is always convolution of this signal, which is the forcing function, with the operator here. So you, whatever you have here, you convolve with this fixed processor coming from your differential equation. That's the reason, you can think like differential equations are your processors, and you want to understand the output of a signal coming from this processor, and the output is always convolving your initial signal, your input, with the signal coming from your differential equation. So what is that signal? That signal is exactly this one. So your differential equation gives you a signal, a fixed signal. You put your input, gt, the output is always convolving g with the signal coming from the differential equation. That's the reason, convolution operation is used a lot in the signal theory. But for our purposes, we use it to write our solutions in a simple form by using this binary operation convolution, rather than solving all those partial fraction with the coefficients. All right, so I'm going to finish here. So now we are over with the chapter 6. Next time we will start chapter 10, which is basically about partial differential equations. We will not be able to do everything about partial differential equations. We will just give you a taste for partial differential equations. And mainly, and among all those partial differential equations, we will solve a heat equation. And also, while solving it, we will build a theory of Fourier transform, or Fourier series. Like here, we use Laplace transform, and there we will use Fourier, basically, series to solve the problem, which is another integral transform. Okay, see you next time.